Hello students, welcome back again in the nuclear physics class. I am Abhishek Kumar Chowdary, physics lecturer with Sri Chaitanya. So, we have discussed many important and interesting phenomena of nuclear physics and have done many numericals also on that. In previous class, we were dealing with the concept of half-life, mean life, exponential radioactive equation, the law of radioactive decay. We have done some numericals on that. So now heading towards 180 out of 180 in physics and 720 out of 720 in NEET. The next topic is fission. So today we are going to discuss about nuclear energy. And in nuclear energy, there is an enormous amount of energy released, whether it is fusion or fission. Actually, in binding energy curve, what we discussed, if we are heading towards the middle of the curve, from left or from right, that was, if you remember, it was called exoergic reaction. So when you are heading towards the middle of the curve, from left or from right, it means you are heading towards what? Stability. To gain stability, from the right hand side of that binding energy curve, what they will do? They will split into the stable nuclei, and the left hand side of that binding energy curve, they generally fuse. So starting with the first concept, that's fission. Let's see the definition. Nucleus of heavier element. Binding energy right hand side, if you remember, heavier mass number we are talking about here, splits into two or more smaller nuclei accompanied by energy. This is fission. There is a heavier element splitting into stable nuclei, and some energy obviously will released. That process is called fission. See, fission was first discovered by Otto Hahn and Strassmann in 1939. And what they did? Let's see. This was the reaction. They first took uranium-235 that was bombarded with neutron that we have discussed in neutron. They are preferred as used as nuclear projectile. So see here, this is the target, this is the projectile bombarded. What will happen? 235 and 1 relatively more stable uranium 236. So it is relatively more unstable, so its the probability of decay will be higher as well. So it will decay into, in that reaction it decayed into barium and krypton with this much neutron and obviously some energy released. See, the product is instantaneous. You cannot pre-calculate the product. So it could be any product, almost middle mass numbers are there. So in that reaction they observed barium and krypton and some energy was released. For this particular reaction, the first fission reaction in 1939, about 0.1% of mass of reactant was converted into energy. About 0.1%, we are talking about this much reaction only. In this reaction, 0.1% of the mass of reactant, this is the quite huge mass defect. See, so mass defect, 0.1% of the mass of reactant. This was almost 0.214 AMU. These data are important. A simple question can be asked. In the uranium-236 fission into barium and krypton, the mass defect was, either they can ask you in the percentage 0.1, 0.2, ABCD, 4 options, or they might ask you in terms of AMU also. So these data are important, 0.214 AMU. Energy released, we know that from mass energy equivalence, if 1 AMU is there, what is the energy? 1 AMU multiplied by 931.5 mega electron volt. So for this much amount of mass defect, energy released per fission of U-235 nucleus was this into 931.5, and can you see this? 200 mega electron volt of energy. 200 mega electron volt of energy was released. This was an enormous amount of energy. And this energy, you can see one more thing interesting here. If we are using uranium-238 in place of uranium-235 or 236, it undergoes fission with neutrons having energy this. What does that mean? It means projectile's nature, see neutron is the projectile here. So all nuclei like unstable uranium like 236 or 235 is the basic reactant. Uranium 235, it undergoes the fission with thermal neutrons, or you can say slow neutrons. Uranium 235 undergoes fission with slow neutrons, thermal neutrons, and this kinetic energy you can see is 0.025 electron volts. So very slow, very lesser energy neutron can cause fission of U235. But if you will see, take uranium 238, then students, you need higher kinetic energy neutrons, and higher, how much higher? You can see fast moving neutrons having energy greater than 1 mega electron volt. Oh my god, this much amount of energy it needs to be inside the neutron, the projectile. And if neutron's kinetic energy is greater than 1 mega electron volt, then U238 will cause fission. So basically the synopsis, the basic preface of the fission is heavier nuclei is there, splitting into stable one, releasing some energy. In 1939, Otto Hahn and Strassmann, the reaction was 235 neutron, thermal neutron, U235, slowly moving neutrons. And what was made? Relatively unstable nuclei, that uranium 1, 236, and that splits into barium krypton. But what I said, the product is instantaneous. You cannot be very sure about the product before fission, and some enormous amount of energy was released with a mass defect of 0.1%. These are the data. This is again I am telling you important one, what kind of projectile is needed in what kind of fission. So uranium 238, what kind of? Fastest moving neutrons with kinetic energy more than 1 mega electron volt. And for uranium 235, for this it was thermal neutrons, or the slowly moving electrons. So we have just discussed fission of uranium 235 to 236 by 1 neutron projectile, and then further. Also thorium or plutonium, they also undergo fission. So there are some characteristic points, they are important points, and most importantly question points for NEET regarding fission. I want you all to go through all these points quite properly and with full concentration. See the points. Projectile that can be used to bombard a heavy nucleus, bombardment of heavy nucleus, could be proton also, deuteron also, and alpha particles also. Okay. Here we are using neutron, so don't make a concept in your mind that okay, this is a fission reaction, only neutron can be the projectile. This is not the case. In fission, we can use alpha particle, proton, deuteron, even thorium undergoes a fission by using proton. Alpha particles can also be used. So all nuclear projectiles could be used. What is the actual use there? You have to make that relatively unstable so that it readily decayed into the stable one and fission takes place. So to make it unstable, you have to supply energy to U235, that extra amount of energy that it needs, and that can be provided by neutron or alpha particle or proton, even to thorium also, plutonium also. So these all are also projectiles that could be used for nuclear fission. Next point, thorium 232 Th, and we are talking about here plutonium 239. What kind of projectile they are using for the nuclear fission? Important question point. Thorium 232, it undergoes fission with fast neutrons only, but plutonium 239 you can see undergoes fission with slow as well as fast. So when thorium is undergoing fission, what you need is the fast neutrons, but plutonium both. So it can be, suppose there is a question in NEET, which of the following can undergo fission by using both slow and fast? What will you take there? Plutonium 239. The next point is the fission products fall into the range. See, we have discussed that if fission is taking place for uranium-235, the product what we wrote was barium and krypton, but strontium and xenon, they can also be formed. Other products are also possible there. So what kind of product? I told you that product is instantaneous, but it cannot, like you cannot make sodium there and you cannot make aluminium there. So there is a range defined in what range the product will fall. So the range is, there are two ranges. First, having atomic number from 35 to 43. These all can formed in that fission as product. Atomic number range, do note it down, and atomic mass range. This is the, you can say this is the first range of atomic mass and atomic number. And the second range, like barium, krypton, you can check it out with this. And in second range, this is atomic number 51 to 57 and atomic mass 125 to 160. So these are the basically two ranges. Any product, any combination of these two ranges could be there in a product. And obviously energy will be released. Let me tell you, energy that is releasing there in nuclear fission is released as kinetic energy of the products. Kinetic energy of the products, and also some amount of energy you can say is releasing in terms of heat, in terms of gamma ray. These energy is also there, gamma ray is also there, heat energy is also there, but the major part of energy is releasing in the form of, note it down, kinetic energy of products. Okay. Next point, see, pressure and temperature. These are very high in nuclear fission. Both are very high. High pressure and high temperature. Again a question point. In nuclear fission, suppose I am giving you four options. First, low pressure, high temperature, low pressure, low temperature, like this. What you have to take there? Pressure is high, temperature is high. Both are high. And the next question point, see, there are two types of neutrons I have written here, prompt and delayed. These neutrons are the product neutrons. In that U-235 reaction, if you will see there are three neutrons I have written in the product. In general, in fission, 2 or 3, in uranium-235 I am talking about, at times depend what product are actually being formed according to these ranges. At times you will get 2 neutrons, at times you will get 3 neutrons. So on an average, can we say 2.5 neutrons per nuclear per fission cycle, 2.5 neutrons. More than 99% of these neutrons, they are there, they are formed, they are decayed, you can say, in a time span of 10 raised to power minus 18 second to 10 raised to power minus 15 second. What is the data here? Time span is 10 raised to power minus 18 second to 10 raised to power minus 15 second. These are the product neutrons, and these product neutrons we are talking about for more than 99% of the product neutrons are released in this much time, instantaneous. So what is called prompt neutrons. But approximately 1% is left. This is 99%, more than 99%, not exact data. Approximate we are talking about. So around 1% is the delayed protons. They are released in a period of time, it takes time. But do note it down, those 1% delayed neutrons, they are used in, underline, nuclear reactor. Have you heard about chain reactions? I'm very sure you must have heard this. When in 1945 on Japan, USA dropped that atom bomb, we in our childhood also used to listen to stories that it is radioactive and the chain reactions are there and the ill effect of these radiations are long lasting and all. How this all happens? What is the chain reaction exactly? Try to understand in a very basic manner the chain reaction, okay? What was the fission reaction? One neutron you threw at U-235 as a projectile, and what you got? Product with 3 neutrons. Average we say 2.5, in some product it's 2, in some is 3. But in that particular reaction that we wrote, what we got? 3 neutrons. All those 3 neutrons were also energetic, because the kinetic energy, the energy released in the fission is in the form of kinetic energy of the products. So those neutrons will again act as projectile for 3U235. So at the same time, 3 another U235 will undergo fission. All those 3 neutrons are also energetic. See what we have discussed, the energy releasing in fission, they are in the form of kinetic energy of the products. So neutron is also there, no? So those neutrons are also energetic. Now these 3 neutrons, they will bombard, will act like a projectile for 3U235. And simultaneously all these 3 U235 will also give 3, 3 and 3, 9 neutrons. Then those 9 again 27 neutrons. What is happening here? Number of neutrons increases in geometric progression. Do you know a simple example for this? What is that? An atom bomb. An atom bomb is an example of this kind of fission. So let's see from the basics. Emitted neutrons in fission can initiate other fissions, hereby producing a chain reaction. So what is a chain reaction? Chain reaction is there is a fission. Fission's product is also neutron. Those neutrons are again initiating fission, again neutrons, again initiating fission. See here, this is one neutron bombarding on U235, 92, barium, krypton, fine. But along with them, there are 3 neutrons. Now these 3 neutrons, uranium, uranium, uranium 235, 3 other uranium 235. Again 3 neutrons, 3 neutrons, 3 neutrons. 9, then again 27. That's why we have written that it is increasing in geometric progression. So we are talking about this, and these are again initiating what? Fission. So this is the basically the concept of chain reaction. Now the question is, can we actually stop it? Can we actually control it? Obviously we can. And how? Just slow the speed of these neutrons. Slowing the speed of neutrons. A minimum energy is required, na, 0.0025 electron volt for U235, or for thorium we discussed greater than 1 mega electron volt. For U238 we discussed that. So a minimum energy is there, critical value of energy is required for the projectile neutron. So slow down the neutron below that energy. And how to slow it down? We have discussed in neutrons the properties of neutron. Use heavy water, even normal water also, or graphite rods. These rods, the heavy waters which we are using for slowing the neutrons down, they are called moderators. They are called moderators. We also use boron or cadmium rods for this purpose, for slowing the neutron down. So in reactor what we do? We control chain reactions there. So chain reactions can be controlled by slowing the speed of neutron. So this was the very interesting concept of chain reaction. Now as we know what are chain reactions, they are neutrons and they are initiating again the fission. Hence geometric progression, the increase of neutrons there. Chain reaction, we can control it by slowing the neutron down. These are the basic, we can say a preface of basic discussion of chain reaction. Now in mathematically there is a data, there is a number, there is a ratio that can actually predict what kind of chain reaction will be there, or even chain reaction will initiate or not. So that ratio is called neutron multiplication factor, or also reproduction factor. Neutron multiplication factor or reproduction factor, and factor is denoted by, you can see, K. So what is K? K is number of neutrons in the present generation and number of neutrons in the previous generation. The chain reaction, there was a previous generation, there is a present, then present becomes previous for the next product. So in chain reaction, the before was the previous generation, and right now what is being formed is the present generation, and this keeps on going on, this keeps going on. So what is K? Again, see, number of neutrons in the present generation upon number of neutrons in the previous generation. If this K is 1, it is a fraction, obviously it means number of neutrons in the present generation is less. Previous generation number of neutrons will be greater. So in such cases, when the present generation number of neutrons are less as compared to the previous generation, chain reaction could not be started. Chain reaction cannot be initiated. So there is no question of further fission. So you can see that U-235 initial neutron was 1 and the final was 3 or an average 2.5. If the final would be suppose 0.5, then this is not even a case of chain reaction. So chain reaction cannot be initiated. If K is 1, so initial the previous generation number of neutrons and this present generation number of neutrons, they are matching, they are equal. Obviously there will be chain reaction, but that chain reaction is with the steady state. Steady state that we see where? In nuclear reactor. In nuclear reactor we see the chain reaction with the steady state. So the first one, this K less than 1, this can be said subcritical state. This terminology you students you should know for your objective question. Subcritical state is what? Or in subcritical state, what is the reproduction fee? What is the reproduction factor? That's a fraction. When K is equal to 1, this is called critical state. For example, I told you nuclear reactor. So what state is there in nuclear reactor? Critical state. K is equal to 1. When K is greater than 1, this is called uncontrolled chain reaction. In this, in geometric progression, it will keep on increasing. Example for this, I have already told you, atom bomb. So this K greater than 1, uncontrolled chain reaction, this is called supercritical state. You can also memorize K's value according to this state, critical, subcritical or supercritical. Also, there is a concept called, for fission, for chain reaction, this is called critical mass. Let me show you. There is also a concept of critical mass. What is this critical mass? See, to sustain the chain reaction, it's not like any amount of uranium you are taking and you can start the fission and start the chain reaction. To sustain the chain reaction, there should be a very minimum, very critical amount of mass of uranium. It is defined minimum amount of mass of uranium. And that minimum mass of uranium to sustain the chain reaction is called, it's called critical mass. So what is critical mass? To sustain a chain reaction, minimum mass of uranium is called critical mass. Let me tell you, this is very important as far as the objective, conceptual objective questions are concerned. These are the only data, but they must be in your mind there. The question can relate even the energy according to this data. So enormous amount of energy is being released. So obviously K is one uncontrolled chain reaction. If chain reaction is not being started, then K is a fraction. Also, don't remember the name state there: critical, subcritical, supercritical, and critical mass also. So on the basis of the entire chain reaction concept, we can classify the chain reaction into two categories. The first, uncontrolled, and the second, controlled. Atom bomb, nuclear reactor, destruction, peaceful purposes. So let's see, in uncontrolled chain reaction, more than one neutron causes the further fission. More than one neutron. So obviously if more than one neutrons are causing further fission, the fission rate is very high. Rapid fissions are taking place. More energies are releasing there. So these are the very fast reactions. Almost all the substance, entire the reactant you are taking, they are fissioned instantaneously, very fast. So the enormous amount of energy is releasing that can be used in the weapons, the atomic bomb and all. Here controlled chain reaction. Only one neutron, see this is also chain reaction, but this is controlled. Only one neutron is causing further fission. Only one, more than one is not allowed to do further fission. And in this is a very slow process and energy is releasing with a steady rate, steady pace. So we can use this in a peaceful purpose. Nuclear reactor, don't forget, if question is asking you nuclear reactor, what type of? Controlled. Atom bomb, uncontrolled. So in today's class, if we conclude the entire concept, what we got? We got the concept of fission. First, fission is what? There is an unstable nuclei there. Neutron is getting bombarded. U-235, 236, then splitted. More neutrons, more energy in the form of the kinetic energy of the products. Also some energy in gamma rays and some energy in heat form. Okay. Then fission took place. In fission, there are very important points. I would suggest you to go through all those points, students. Those all are the question points. Like the product formation is not predefined, that is instantaneous. What is the range of atomic masses and the atomic number in which the uranium-235 the product was formed. Again, there was some fission in which slow neutrons were used. There was some fission in fast neutrons are used. There was some fission which can be caused by both slow and both fast. So you have to remember what type, where what kind of neutrons are being used. Then again we were discussing the concept of chain reaction, the geometric progression, the controlled, the uncontrolled, then the reproduction factor, comparison of neutron, K fraction, K equal to 1, K greater than 1, critical mass. Then we discussed that the K is according to K you can say the critical state, the subcritical state. So these were the final, these were the conclusion that we did today. Let me tell you, it was a bit theoretical topic, but nevertheless the questions are very important, questions are being asked on this. And these questions, these objective questions will be there. You can be able to do it only when you are very strong with the fundamentals. So let's move towards the goal of getting 180 out of 180, I am repeating, in physics, and 720 out of 720 in NEET. So God bless you with that. Happy learning, stay healthy and keep doing nuclear physics.